conversation and show me with your eyes looking up here up front that you're finished. And if I could get a little spot for my helpers right here, we're going to keep on going. So let's go ahead and keep going. Yeah, are we good? So, why does that work? That's the big question, right? And there, I'll put on your screen some of the characteristics that you might have just talked about with the person next to you. Things like this. The fact that the teacher presented all of that information, very small steps. Each thing that he taught was in a particular order. It was sequential. Uh, just a little bit of information presented at a time. The other thing was that each of his directions were clear. It's just better to be clear than unclear, of course, but the importance of an unambiguous presentation, right? A lot of times in teaching, we can add in lots of extra extraneous information that's not necessary, really quick and to the point, minimal statements, and alternating between the teacher presenting something and the student doing something back. So we have this interactive type of presentation where it's just a little bit of teaching and then the student must do something and then it's back to me, the teacher, and then back to you. A lot like a tennis match, right? You serve the ball and it comes back to you and we get this kind of back and forth interaction. The teacher corrected errors and didn't let the student continue to make the same mistakes. We live in a world in education where it's kind of popular to ask kids, well, what would you have done differently? And a lot of times, that's a good question to ask. But in other times, it's not because we know stuff. We know how the content works, and we know what misconceptions can be embedded if we're not very careful to correct errors before they become embedded in the long term. And of course, most of what you saw was practice, right? Most of the lesson was the student doing stuff actively, being involved in it. Learning is not a spectator sport, as I said earlier. And then the mats, if you notice with the mats, how they pulls off these mats, that's such a great metaphor for great teaching, where at the very beginning, it's highly structured. We don't want the kid to break his neck and become injured. So there's very, very careful supports in place at the very beginning, and towards the end the students doing it entirely by themselves. And this is where you get motivation. This is where the feeling of success, the feeling like I can freaking do this, right? I can do something I wasn't able to do before, that really gets people, it really solidifies sort of a self-concept in each student. I am I'm smart. I'm amazing. I'm special. Look at me go, right? Um, well, researchers have a word for this. They used to call it direct instruction, and then over time they switched it up. And nowadays, this pattern of behaviors is called explicit instruction or explicit teaching, an approach that is unambiguous, that is presented in small steps, that involves modeling, practice, and feedback in a way that involves the learner so that the student can eventually do really great and powerful things. And a lot of people just call this just good teaching. It's just what the best teachers do. You think back to the teacher who really supported you, who, for me, that was a teacher who taught me Math 90, which is like the math class that's sort of remedial when you get to college because you have to pass a math class. I spent a lot of time overseas and in France in particular, and I didn't learn a lot of math, and I skipped a lot of math classes. And I get to Math 90, and I get this teacher who could just explain anything just so darn clearly in a way that made sense. And and he did it in such a systematic way that and I owe so much to this person because he made something that was hard feel easy, right? That's what I associate with the best teachers, right? Well, the argument I'm going to make today is not only that explicit instruction is like rocket fuel for learning, not only that it's efficient and that it's effective, but that it actually is designed based on how students learn and the cognitive architecture that's in each of their little heads and their noggins, uh, how they learn interacts with explicit instruction in wonderful ways. And there's a reason why it's so effective. It's because it's based on how they learn. Now, I'm going to go ahead and model kind of how the mind works by focusing in on sort of a wine bottle metaphor. And I've heard Israeli wines are very good, so I'm sure you'll understand this metaphor. It just seems to sink in whenever I use this wine bottle metaphor. But basically, we know that kids need to learn stuff. They are thinking beings and they need to acquire lots of great information. And all that information's out there. It's in the textbook, it's in the PowerPoint presentation. Right now, I'm speaking and you have to work with what I'm saying in a space that is very fragile called working memory. And working memory as I mentioned is very limited. Right now, some of you are dealing with probably these simultaneous translation issues, and you got the person next to you who's on their phone, and you're thinking about all these different things, and then I'm talking and I'm explaining, probably talking too fast, and I'm trying to slow down, and I'm trying to teach you in a way that I will help you learn this stuff, and you've got to deal with all of that in your working memory. And the problem is that working memory is very limited. It's like a bottleneck in the sense that whenever I teach you something, it goes into this working memory and it can very easily be clogged up if we're not careful about what goes into it. If we don't teach in a very systematic way, if we don't teach in small steps, if we present way too much information, that working memory system, that thinking processing system can get overloaded, jammed up, and learning doesn't take place. And what is learning? Learning is just simply a change in long-term memory where a student can knows different things. And this long-term memory here is infinite in the sense that we don't know what the limits are of what can go in there, but as long as we can give you the right cue, things can come back to any of us, which is why, when I think back to when I was in ninth grade, the song that was most popular was Usher's "Yeah." And right now, me saying that, you might think back to when you were in the first year of high school in ninth grade, when you were, 11, 12, 13. What was the most popular song then for you? All of that's in your long-term memory. And so, however I teach, I need to honor this cognitive architecture to really ensure that students get it. And often we don't do that. A lot of times we do, like, to show the fragility of working memory, people will do like a working memory test. I'll kind of do just kind of a very quick version of it. If you take a look right here in this space, the space I'm kind of hovering around, I'll put some numbers up. And I want you to try to remember all of them. You can't write it down. You can't use the person next to you to remember half of it for you. Just go ahead and try to lock in right now and try to remember all of these numbers as I put them on your screen. Now, how many can you remember? I mean, if I ask you to say them forwards, it's probably a lot easier. If I ask you to say them backwards, how much harder that is. If I start right now, if you're all holding this in your mind and I start telling you about when I was a kid, my phone number was 475-6314, area code 253, and all of you are going, wait a second, I'm trying to hold in this working memory all of this string of numbers, and you're bombarding me with more information, and I have to take that into consideration while also holding in mind these other numbers, and it becomes this impossible task. By the way, if you had to repeat the numbers back, pat yourself on the back. If you did it in reverse order, this is the order of the numbers. And that experience, I love to give that to students. The experience of like what it feels like to have your working memory overloaded by instruction that isn't tailored or designed appropriately, that isn't broken down sufficiently. It doesn't just work with numbers, it works with everything, with learning how to write a 5-paragraph essay and knowing that all the different parts have to be coordinated, doing a really complex math problem where each of the steps is dependent on the last step, reading really complex text. And if you really think about it, school is filled with really difficult and challenging tasks. And when I look around to my students and you look around and you kind of start to empathize with them when it comes to their daily lives. Actually, in the old days of the old Chat GPT, I typed in for this picture into AI, I typed in kids acting naughty, and then it put a bunch of devil's horns on some of the kids' heads, if you can see it right here. So I kept in the picture. I thought it was funny. But if you think about the kids here, you think about the, students who forget certain steps after you just taught them, kids who start to show frustration over what's happening, kids who are confused and overwhelmed, making simple mistakes. I'm feeling frustrated. Why don't they get it? Why are they showing why are they disengaging from my lesson? What is going on here? Kids who avoid tasks. You can see that cognitive overload, the feeling of working memory being overloaded, can be expressed in so many different ways. Giving up quickly, saying I'm just not good at this. I recently had to take an IQ test for a job I was having. I had to take one of those kind of online proctored tests, and I felt just like this, in the sense that a lot of what I learned in my life just didn't apply to this task. The spatial reasoning tasks of having to grapple with so many different multiple steps and items in working memory. It's and kids sort of expressing that by messing around, by misbehaving. It's just so much easier to try to be the class clown than it is to be perceived as stupid by your peers. And I say that in all seriousness. One of the things that we could do is we could just blame children for not understanding things, but a much more productive and humane way would just be to fix the instruction, to make sure that if they're not getting it, that means I didn't teach it right. And that always being in a state of revising and iterating and thinking about how instruction is just designed to make it so that every kid gets a chance to learn it, not just the kids that came to school already knowing how to do it, not just the kids at school that have parents helping them or they do Kumon after school, but all kids having a chance to access this, including the kids that came from the other side of the tracks, including the kids that I got into education to serve, those that struggle with just for things that you and I take for granted, that we just find to be very easy. So working memory is very limited. That's obvious. And a lot of what we're teaching is just like this big green ball here. It has so many different parts and so many different steps. School's not easy for everyone. And the very first sort of line of prevention, in my view, is really to decompose very complex material into its parts, starting with just the idea that when I'm going to teach something, I'm going to teach it. I'm going to think of these complex skills as just smaller atoms, and I'm going to teach those parts separately and in isolation, and then I'm going to slowly recombine them so that the kids can all access the material. I'm going to put a math problem on your screen. This math problem right here is one that I've taught many times to kindergarten students. And to you and me, it looks very easy. We can all just immediately say, 4 plus 3 is 7. But for a child who's just learning this includes a lot of steps. Steps you may have forgotten need to have been taught. And it's just like the backflip. That backflip, when we taught the kid in the gymnasium, includes a lot of steps. And those steps need to be taught in a systematic and sequential way. Using a direct and explicit instruction approach is extremely beneficial when they're first learning something new. This is how the skill ends up having to be, by the way. The child needs to start with the number 4, and then they need to be able to either count on their fingers or draw lines or draw dots. And they need to say 4, 5, 6, 7, and write a 7 in the box. Real quickly, what are all of the component skills that go into this? What are all the things a child needs to know to be able to do this skill, which, by the way, takes like 30 or 40 lessons to teach in kindergarten if you coordinate all the parts and you take your time with all of the different components? What are all of the different parts to this math problem? Well, the first thing you might recognize is that this is not even the first skill. The first thing the child needs to be able to do is to be able to go 1, 2, 3, 4, 5, 6, 7 with a line or a dot for each number, and then write the 7 in. Sort of addition the slow way. The counting on strategy is much more advanced. It takes a lot more practice. You might also, well, now look at this. We've got these lines that they've got to draw. Kids come into kindergarten not being able to count objects, much less a task like this, where the lines are separated in space. So what does every child do when you give them 4 lines here and 3 lines here? What do? They go like this. 1, 2, 3, 4. 1, 2, 3. That's all. Seems like all kids do this. And you have to teach them how to count the lines. And you need to teach them how to coordinate their finger and touch and say the number at the same time. And then when the lines are separated into 2, they can count the 2 groups of lines as by counting on from the first one. We have these lines. Another thing that they need to be able to do is to draw them. And children come into school with not being able to hold a pencil. Some kids do and some kids don't. I got into teaching to teach everybody, not just the kids who come to school already knowing how to hold a pencil. So we need to practice doing things like this. Practice drawing lines for a given number. If I have them do it here, at first, what's going to happen? They're going to become overwhelmed. It's going to be too difficult. So let's practice doing things in isolation. Well, you notice that it said 4, 5, 6, 7. That's a skill that's done initially verbally. I say 4, 5, 6, 7. Count on from 2, everybody, and stop at 5. 2, 3, 4, 5. All right, class, let's start with 3 and end up with 8. Get 3 going, 3, count. 4, 5, 6, 7, 8. And the kids need to practice that before they even grab a pencil, because they can do it so early if you just start practicing it on the carpet. Practicing this every day is part of a routine, because one day it's going to become part of this skill of how to work an addition problem. You may have noticed that there's an equal sign here. There's a plus sign. This is all symbol identification. And they must learn this rule. You must end up with the same number on this side of the equal sign and on the other side, because addition is really about balancing 2 sides of an equation. That's how you operate on problems, not just addition, but all the operations. Students come into high school sometimes and they're given multi-step equations, and they don't even know that the equal sign means that both sides need to be the same. They think that the equal sign means put the answer over here, which is not correct. You can teach children this rule very early on, from the very beginning, doing tasks like this, where I say, is 4 the same number as 1, 2, 3, 4? Yes, it is. Is 4 the same number as 3? Kids say no. What about these lines and 7? Is this the same number as on the other side of the equal sign? That's right, because you must end up with the same number on this side as you end up on the other side. You can teach that to kindergarteners, and you can teach it to anyone as long as you use explicit instruction in a systematic direct instruction design. Now, we need to get kids reading the equations and practicing reading from left to right. We need to get them to be able to write their numerals. Kids come into school not being able to write their numerals. So what do? We teach them, and we teach them not just implicitly and sporadically. We teach them systematically, just like we teach them how to do their alphabet. We teach them how to write their numerals. And what all that leads up to is just this amazing design, just with this one problem. And it's the same with the backflip. And that's that all of these pre-skills that we teach kids, all of these little components, they start in isolation, but then we kind of weave them together. We weave them together and we coordinate them and we integrate them just like a rope, different strands of a rope going together. And what started as an isolated skill becomes an integrated skill. And what started with me teaching it to you and showing you how to do it, it becomes a skill that they can do by themselves. And over time, you blend and you weave and you're so careful and you're thinking about every single kid in that class, down to the kid who comes into your class, not feeling like a mathematician, not feeling like math is within their reach. And you get to this point right here. And right when you get to that math problem and you say, count on from 4 and write the number in the box. And all kids can do it first time. For me, that's the power. That's the power of what we hold as teachers. And it's the power of explicit instruction. It's the ability to get everybody to learn really hard stuff in a very short amount of time, and in a way that feels supported and feels motivating and feels it feels like you're getting somewhere, that you're making progress, that all this, I feel like a huge sense of purpose as a teacher, but also as a student when you're in a class in which everything is thought out and is so intentional in this way. And so back to our working memory model, we know that working memory is very limited. And we also know that long-term memory is effectively limitless. It's unlimited. And this long-term memory is what enables us to do really cool stuff in our lives. What I have on your screen, it says that long-term memory bypasses working memory, meaning that once you know something, it's no longer necessary for someone else to explain it to you, to teach it to you. It's now time for you to practice it. It's now time for you to use it, to go out and make a difference in this world with the stuff that you've learned. And long-term memory is sort of, in a way, our superpower. If working memory is our limitation, we have a limited bandwidth and a limited capacity to process lots of information at a time. Long-term memory is what enables us to think critically and creatively and go out and problem solve and tackle difficult problems, so long as we have the right skills embedded in there. I think of another thing that I don't know how to do very well, which is how to use Excel. I had this task given to me very recently. It says, use Excel to calculate the total sales per region from a data set, then create a bar chart to visualize the results. Maybe in the era of Chat GPT, this is quite easy, but doing it by yourself when you don't know how to use Excel, especially if what's in your long-term memory is so limited here, and you just essentially have insufficient prior knowledge, this is a struggle, and it's very demotivating and very frustrating to do tasks that you don't have any of the prerequisite skills to do. However, um, and this sort of describes kind of how we think about long-term memory. Um, the behaviorists don't need to think about these things, but I like to think about them once in a while, which is that, with students, when they're just learning something new, they really don't have many long-term memory resources to draw upon. They're like me with the Excel spreadsheet. They don't even know what the functions are or what the different those different shortcuts and equations that you can do in Excel. They don't even know how to use the software at all. And for math, they don't know the prerequisite skills and the pre-skills. And for writing and reading, they don't know their phonics and their phonemes, right? But when you go up into, sort of looking at a child who achieves a level of expertise, when someone actually knows something and can bring something to bear to solve that problem, how easy things become. Like if you know these things that I put on your screen, I assume they're correct because I've been relying more and more on AI to do my thinking for me. The If you know all of these things, doing this task, you can finish that in seconds, not hours, not weeks, but seconds, right? And because you've automated all of the skills and long-term memory, that it allows you to bypass all of the working memory limitations that you might have to be able to tackle really complex problems. So this is basically why phonics works. And in the United States, we don't have the wonderful opportunity to learn Hebrew, but we have to learn English. And English isn't a particularly transparent orthography in the sense that lots of words don't follow the same patterns, but 70% of them do. We have 44 phonemes or sounds that map onto letter correspondences that if you memorize these, if you essentially practice with kids until they learn them, they can read most words, right? And for the longest time in the United States, there were all of these wars and battles over, should we teach kids this way? Should we have them learn or memorize certain parts of words? And the experiments that happened on children were at first for science, and over time we learned very quickly that the best way to do it was to teach them explicitly and systematically teach them their sounds, because you and I can read Sam can pat the cat sat on the mat very quickly with very minimal effort, but a child needs to have explicit direct instruction in these things, in short vowel sounds and blending in consonant vowel consonant words. They need that instruction. This is why phonics as an instructional approach has been shown to be so effective. And there's increasingly in the United States consensus that this is the best way to approach teaching reading, and yet so many teachers are not trained in this method. And even and we're not talking about just older veteran teachers. We're talking about new teachers coming out of university who are tasked with teaching your child how to read, and they don't know how to do it, or they're even told, give the kids books, let them try to figure it out, let them discover the love of reading through lots and lots of text. And it just doesn't work. It doesn't work, just like it doesn't work for the backflip, and it doesn't work for the Excel spreadsheet. It doesn't work for anything. We have a similar problem in the United States around math, in the sense that for some reason when you're teaching reading, it's okay to teach explicitly and systematically, but in math, let's give them lots of materials. Let's let them play with lots of objects. Let kids circle around the classroom and teach themselves math. And it's really wrong. It doesn't fit into what we know with how the mind works. If you think about the same thing as Sam and the cat and patting on the mat and the number, in this problem, 378 times 873. It's a lot of numbers. It's a lot of steps. It's hard, except it's not hard for me anymore. I can do this problem in just a few seconds. And it's not hard for you either, as long as you remember some of these things. For example, your math facts. Many teachers, as I go from school to school, tell me that they are being told that they're not allowed to teach these facts, that these facts will hinder children's love of math. And it's no different than what we used to say about phonics, and it's no different than what we say about a lot of things in education. We just have the wrong mental model of how the cognitive architecture, how this working memory and long-term memory cognitive architecture works. And so kids pay the price is what ends up happening. Because if I teach them these facts very clearly and systematically, and I teach them the algorithm for doing multiplication, long multiplication, and I get them to practice those things a lot, they can do these problems in seconds, and they can feel really good about themselves doing it. So here's a few of the principles we've gone over, just a bit of a review. So we know that we have this structure called working memory, and it's like a bottleneck. It's extremely limited. We have to be extremely careful when students are brand new to a topic that we teach things with incremental introduction, just carefully and systematically. It doesn't mean slow down the pace. We have no time to waste, right? These kids came to us and we need to teach the heck out of this stuff. But what it does mean is that we need to empathize with children when they're just learning something new, that this big thing that is easy for you and I, it's not easy for them. It's not easy for them until we teach it right. And we have to be very careful about the instructional design that we apply to our learning materials. We also know this other thing, which is that long-term memory overcomes these working memory limitations. Once the child knows it, they're able to do stuff with it, and they no longer need the same strong supports as an expert that they needed when they were a novice, when they were just starting out with the material. And finally, this is what explicit instruction is. and explicit instruction is designed from these principles. It's the way to get kids to go from novice to expert in anything very quickly. So let's dive into that last idea. Like, what is it? What is direct and explicit instruction? And for those of us who've been in education for a long time and we've seen the pendulum swings, you might see this and go, yeah, that's just good teaching. That's what I've been doing. But certainly some people have been told not to do this. Explicit instruction begins with modeling, which is the basis of my book, Just Tell Them. It begins with teaching the kids something, demonstrating it, but always in very small incremental steps, not these long-winded lectures, not these 15, 20, 30-minute monologues, but very quick, minimal statements. It then proceeds from an I do phase where I show you how to do something and I do all the cognitive lifting to you doing it, but you're doing it with me. I'm not just going to throw you into the deep end of the swimming pool and watch you drown. I'm going to make sure that you have all the supports that you need, and I'm going to check that you understand all of these things before you move on. If you don't understand it, it's my job to help you. It's my job to get you there. And so I'm going to be just as involved in this as you are, as we partner together to crush this, right? To crush this new academic thing so that you can learn it. And then finally, as I go through the full phase, it ends with a you do phase, sort of an I do, we do, you do, in which the child now does lots of problems by themselves. And I can step back and right now and I can circulate. I can look into my classroom and I can check in on the kids who need it most. I may even pull a couple of kids who still don't get it to my back table, and I teach them. I teach them more intensively, or I get to go around and collect information from the class, pause the class, and teach everybody together again, and then we're back into independent practice. But what I'm also doing is I'm praising them, and I'm going around and I'm saying, "Look at you, look impressive." Akaika's on fire. Sally's on fire. And as I'm walking around, we're celebrating because look at what we're learning. Look how fast we're going, right? And this follows this very intentional design known as the gradual release, where it begins with the teacher providing information, but it ends with the student doing the backflip independently. Now, and that same thing follows some of these same concepts I've been bringing up of novice to expert, where we take you along all the way and we take responsibility to getting you there. But in the end of the day, look at you go. You can do it by yourself. Let's take a math example, since I love teaching math. We start with the beginning, and guess what? I'm going to model some stuff for you. How am I going to expect that you know and can figure something out on your own if you've never seen how an expert does it? You've never been given an explicit or efficient strategy for how to do it. So I'm going to teach it to you, and I'm going to teach it to you well. I'm going to do it with enthusiasm and with an emotion, and I'm going to be inquisitive about it, and I'm going to make eye contact with each and one of my students. But yeah, I'm not going to apologize for teaching them, right? And then as we go along this process, slowly, I'm going to start omitting steps, taking away some of those scaffolds, some of those supports, one at a time at first. And I'm going to start combining steps. I'm going to start passing it over to the kids. Here it is. You do it. You do a little bit more of it. Now you do the whole thing. And for those of you who need more support, here I am. I'm here to support you. And I'm not gonna let you fail. Over time, researchers have sort of started to codify some of these strategies, like these that I put on your screen around this idea of managing cognitive load, of managing the load, the working memory load that is imposed by the instructional design. Things like making sure that you cut all the non-essential information, that you make sure that you're not saying lots of extraneous things when you're talking, and you only present the essential information. So many lessons that I observe, there are just far too many distracting anecdotes and tangents and side stories and things that get in the way of learning. Cut that stuff out. It's not helpful. But also the idea that novices, when they're learning something, it's a very fragile time. Break it down even more than you think you need to. We often overestimate what a child can do when they're first learning something new. And what does that end up doing? It means we have to rewind and go back and try it again. And we're always confused. And it's often the expert teachers who learned this the hard way. They tried something out and they realized they just taught it. They presented too much, and the kids couldn't keep up with it. So the next time they did it in a more granular and incremental way, but only after having tried it on the first group of kids, right? Making sure that we use very concrete examples, worked examples, completion problems, giving students a view of what an expert's thinking looks like through think alouds, demonstrations, very, small, quick, to the point presentations that really teach this stuff. being able to give students lots of opportunities to practice what they're doing. In education, we call that pejoratively, we call that drill and kill, where we give kids, we're gonna destroy their motivation if we give them too much practice. But that's not how it works, and that's not how kids think of these things. Sure, practice is a little bit boring sometimes or arduous, just like it is on the soccer pitch or on the baseball field. But through lots of practice and repetition, it starts to become who you are. And it starts to be something that feels good, doing it and being successful every day. And you start to create a culture in your classroom around mastery and around excellence. And finally, that gradual fading of supports. I see the time that I have. I'll just go ahead and kind of go to the kind of the last the kind of the last bit of the metaphor, which is that it's our job to get every kid to achieve their dreams. And I believe so much in this idea that it's really our job to get everyone to reach their maximum potential as a teacher. And I'm thinking about all of my students and how I at first do all the heavy lifting as the teacher, but I slowly put it on them to achieve it, and how successful it feels to be that student who's supported that way. And I feel like in a way, instruction, the way we teach, needs to be talked about more than it is, at least in American education circles, because it's sort of for me, it's the social justice issue of our time. Is that we live in a time in which there's basically the educational lottery. I am going to send my child into kindergarten, and I could get a teacher who's basing their decisions on evidence and the science of reading and the science of learning, or they could draw the short end of the stick or the wrong straw and be in a classroom in which all of these old ideas of how to teach and how kids learn are still in that classroom, and they're not going to make as much progress. And they might, depending on the child, they might fall behind. And when they fall behind, they're just not able to keep up for the rest of their education, because they're just always struggling with their head just a little bit below water. So let me summarize and let me kind of wrap up here. This picture here is, students going to college, and where I live, college costs, I don't know, $60,000 to get a degree. And after that, you need to, and all of that to get a house that's over here costs probably $800,000 to $1 million to live in a nice neighborhood. And that means you need to get a job, and you need to have a job that pays well, perhaps $60 to $100 to $120,000 salary is going to allow you to buy a house in a nice neighborhood, and it's going to be able to allow you to pursue a career that really matters to you. But you can't do that without a great education. And so here's kind of a summary of what I just talked about. All of our students, they have a limited working memory, and it's easily overloaded. Okay, we know that our bandwidth, our processing system, it's not even really controversial. That it's just we can't handle too much information at once. But we also know something else that's sort of underrated, and that's that the way to bypass this working memory system is by building up knowledge and long-term memory. If the child knows it, it doesn't impose a burden on their working memory. They can do it easily and fluently without much effort. And the problem is, folks, students come to school with different working memories, and they come to school with different amounts of knowledge. And we really, as a teacher, we can't really control that. I mean, I'm just given the group of students that I have, but I know that some students don't find learning easy. They're not teacher proof in the sense that they can just learn if you throw books at them. They need great teachers who are teaching like their pants are on fire every single moment of the day. And we have kids who come to us who, unfortunately, their parents don't take them to museums and don't take them to Paris and don't talk to them about all these really great things. A lot of the students that I work with, they just don't, they come to school, and the place to learn that is here. It's where the teacher is. And we have to take that responsibility seriously. And so to close the gap between, the kids who know all this stuff, and they're advantaged, and those that are disadvantaged, the kids that come with fewer resources, to be perfectly frank, we need to teach this stuff as efficiently and effectively as we know how. And we need to draw upon the evidence base that's available to us to make the best possible decisions. Because each of these kids only gets one shot at an education. And so, in my view, in my reading of the evidence and in looking at how the mind works, how the mind processes information, our best bet is really through effective, systematic, explicit instruction. And if we embrace that, if we embrace a method that is tried and true, that with my students it freaking works, and if we embrace the evidence based around great teaching, we're gonna see a lot of really happy kids, and we're gonna see a lot of kids going to college and pursuing their dreams. So that's all for me. Thank you so much for coming. I really, really appreciate it. And